Okay, number 7. What is the necessity of the extension from natural number to the integer set z? So z, integer gz, it's a German word. It's Zahlen. Okay. I lived in Hamburg for 3 years. Okay, this is a very crucial definition of integer. There are many ways to define integer, but it is a very useful because we make use of definition to find a general solution of a sequence that is called the mathematical induction. So 0 is an integer. If n is an integer, n plus 1 is also integer. And if n is an integer, then minus n is also an integer. It's additive inverse. So additive inverse results in the answer to be the same as additive identity. This is true for the multiplication, so multiplicative inverse results in multiplying multiplicative inverse of a number will result in a multiplicative identity. That is called unity. So using this, I can say some number is equal to the other number by subtraction. I can say some number is greater than the other number or smaller than the other number using this way. Multiplicative identity is 1, and if you repeat the addition by the same number by m times, then the result is m times n. That is, a repeated addition is represented by the multiplication. Okay, so reordering those numbers in a very simple calculation in terms of unities, then you will find that multiplication is a commutative. Tedious, trivial, but very important fact. So everybody knows the multiplicative identity is a unity. Multiplicative inverse for any number that is non-zero, it is just 1 over something. Okay, using this manner, we can find a very simple number system that is closed under addition, subtraction, multiplication, and division, except for the case divided by 0. That is called a rational number. Rational number does not mean it is a rational, it is a logical. It is just, it comes from ratio. Its a root is a ratio, a number that can be expressed as a ratio of two integers. That is called a rational number. However, in a number line, if you choose any 2 points, 0, that is a origin, and unity, then is there any point that cannot be represented by this rational number? Yes, it is, mathematically. Physically, it doesn't matter at all. I don't care whether this number is a rational number or irrational number. Because if we measure some physical quantity, we do not have any ruler that has the accuracy, arbitrarily small accuracy. It's impossible, practically impossible. So I don't care whether this number this real number is a rational number or not. But in mathematics, it does matter. So it doesn't matter in physics. So that is a crucial difference between the mathematics and physics. So these problems are very simple to solve. So I think uh, I can leave it up to you. So, okay. This is also a very interesting problem related to the homogeneousness and the isotropy of space. If I have a one-dimensional object that are aligned on a single straight line, then we can choose an arbitrary point as the origin. The choice of origin can be arbitrary. So it depends on you. So if you want to solve the problem conveniently, you had better choose a reference point that is the origin to be the simplest, as the simplest as simple as possible. However, it doesn't matter. It doesn't matter. That is because the Euclidean space has the translational symmetry. So regardless of whatever amount of translation you have made along the straight line, you shift this origin to another point O prime, your final result should be independent of choice of point. In addition, because the space is isotropic, even in one dimension, isotropy means go to the right, go to the left, they are equal. So you can either choose this a positive x-axis or this part to be positive x-axis. It doesn't matter at all. For convenience, you can choose at any point. By the way. So our nature is approximated as the Euclidean space when we study Newtonian mechanics. However, nobody has traveled far away. Even we do not know what infinity is. Somebody would say the universe is closed. Somebody would say the universe is open. Nobody knows. If you want to test it, if you ride a very fast rocket, you will die before you return. You will die before you detect whether it is the end of the universe or not. So we have never tried to get the infinity, and it is impossible. That's the reason why we abide by the postulate. What's the postulate? Assumption. But it is not a stupid assumption, but a reasonable assumption that nobody has found its counterexample. So in mathematics, they say it is axiom, but mathematics, axiom doesn't fade at all. In physics, equivalent to the mathematical point of view, we say it is postulate, and that postulate may break down. A postulate breaks down, then new theory begins. And Newtonian mechanics is called Newton's first, second, and third law, but everybody knows that it is not a law at all. It's wrong. It is correct in a specific, very tiny region. And it is true that special theory relativity of Einstein is a law, but nobody says it's a law. Why? That's the difference between the mathematics and physics. Physicist doesn't say I'm correct. I try to make a correct statement. However, I have never experienced everything in the world from the beginning of the nature until the end of the nature. Our life is too short. So Physicists claim that we study if we find the truth, and the very basic truth, we would say we have found the postulate from which all of the known facts are well described in a systematic way. So that's the big difference between the mathematics and physics. Mathematics never fails because it is artificial human product. However, physics depends on nature, and nature we do not know very well. That's it for today.